Okay, what we're going to do here is we are going to continue with this example. Like I mentioned earlier, we're going to finish this off for you guys to see how this goes. We're working with this question 23. We're going to integrate by using integration by parts. So this is going to be uv minus integral v du. Okay, so let's make sure we get these other answers. So du will be 1 over x dx, since u is the natural log of x, and v is the integral of, looks like it's going to be x to the minus 1/2 dx here. Okay? Which is x to the 1/2 over 1/2, or this is really 2 square root of x. Okay. So continuing with this problem, using integration by parts, we now have u and v, so it looks like this will be 2 square root of x natural log x minus the integral of 2 square root of x, and then du is 1 over x dx. So we're using integration by parts here. All right, let's see. We do have some audio, so let's double check. Okay, IBP. Two square root of x natural log x minus 2, and then we'll have square root of x over x dx. Just to kind of remark, this integral is going to be 1 over the square root of x dx. Now, if you want to see the algebra that we're talking about here, okay, properties of exponents, just so you guys know, x to the 1/2 over x to the first power is x to the 1/2 minus 1, or x to the 1/2 minus 2/2. You get x to the negative 1/2. And that's why this is 1 over really the square root of x. So I'm going to change that here and just use the, well, we're going to leave it like that for now. So you just want to know that this is 1 over the square root of x. Okay, that's where it came from. Let's get rid of our scratch. Just use properties of exponents. But if I'm going to integrate, I'm going to write this as a exponential with a negative power. Okay, so that integral is going to be 2 square root of x. So altogether, we have 2 square root of x ln x minus 4 square root of x for that integral, because we had a constant here of 2 already. 2 times 2 is 4. So we have to evaluate this again from 1 to t to 1 over, well, got to apply the limits. Okay, t1. So we need f of 1 minus f of t, which is 2 square root of 1 natural log 1 minus 4 square root of 1 minus 2 square root of t natural log of t minus 4 square root of t. So natural log of 1 is 0. And we end up with really negative 4 minus 2 square root of t natural log t plus 4 square root of t. So double check, because we are going to subtract there, which distributes the negative sign. All right, just double checking everything. Looks good. Okay, now remember, we have to take this limit now as t goes to 0 from the right. Okay, so I'm going to get rid of everything we have here. Got to take that limit as t goes to 0 from the right. So now we'll look at this limit. T goes to 0 from the right, negative 4 minus 2 squared root of t, natural log t plus 4 squared root of t. Now, by properties of limits again, limit of a sum and difference is difference of sum. Well, limit of a sum is a limit of sum is a sum of the limits. Limit of a difference is a difference of limits. Limit of a constant is a constant. In other words, by properties, we're going to end up with this. Just using properties of our limits. Okay? Okay, so this is going to be here 0. And then here we get 0 times negative infinity. So don't forget, though, that first limit really is the limit of a constant here. So that constant negative 4 is there. So I think, again, the focus is going to be here on the fact that we have an indeterminate product. Okay? So we're going to have to fix this by using properties we learned from working on L'Hopital's rule. So this is an indeterminate product. So, okay, remember we got to fix this here. So I'm going to change colors. And the fix is going to be writing this first function as a reciprocal in a denominator. Remember, they're equivalent there. This is an indeterminate product that we're looking at. All right. What that means is, as we apply the limit, it looks like it's going to be negative infinity over, so that's the limit of the numerator. The limit of the denominator is, well, t is going to be going to 0 from the right, means t is positive. So it looks like that'll be positive infinity, because t is going to 0 from the right, getting smaller, smaller, and smaller. So the reciprocal is getting bigger, bigger, and bigger. This is where we can apply now L'Hopital's rule. So by L'Hopital's rule now, I get the derivative here of the natural log is 1 over t. So we're going to want to note what the derivative here of t to the minus 1/2 is. Okay, so we're applying L'Hopital's rule. That's going to be negative 1/2 t to the minus 3/2, or negative 1 over 2 t to the 3/2. So negative 1 over 2 2t to the 3/2. So we're going to have some more algebra to do here. This is what we, applying L'Hopital's rule. So let's do some of that algebra now. 1 over t divided by negative 1 over 2 2 to the 3, t to the 3 halves, which is 1 over t times, flip this over, 2t 3 halves. And that's over 1, which is really negative 2t to the 3 halves divided by t. And this is t to the first power, so it's negative 2t 3 halves minus 1, or simply negative 2t. Don't forget this is 2 halves. That's 1 half. Okay. So we're applying, by L'Hopital's rule, that limit as t goes to 0 from the right of negative 2t to the 1 half, which is really negative 2 square root of t. And this limit is 0 now. So we found this limit to be 0, which means our final answer here is really just going to be negative 4. Okay, so we had an indeterminate product to apply L'Hopital's rule. And this is convergence because the improper integral here equals negative 4. So let's get rid of this and get rid of all of this here so we can kind of emphasize what is happening. Okay. So the area under that in this region here equals negative 4. And negative 4 is a nice finite value, which means our improper integral converges. That number is finite. So this area here is negative 4. So it looks like the curve gets really close to that asymptote at x is 0, that vertical asymptote, fast enough so that those approximating rectangles we have a finite area is what we're saying here. So the area is finite, and negative 4 is a nice finite number. Okay, so this is 23. I didn't want to share that with you guys. You guys can take a look at that. This is kind of where we ended up with, but I'm having so much fun. I think I want to try the next one too, and I'll send this to you guys. So the next one is the natural log curve over the interval of 0 to 1. And let's remember something about the natural log curve. We have a vertical asymptote here at x equals 0. So if we're looking at the interval from 0 to 1, again, we have a left endpoint discontinuity. This is for the natural log function, and you're really looking at this right here. So we do have a discontinuity, a left endpoint discontinuity. So we're going to have to let the left endpoint be t. Not 2, t. It's going to be the limit as t goes to 0. Again, we're going to have that t here. If we can draw a straight line, let's do that here. Trying to find the area there. This is where our t will be. And this is the I of t we're looking for. So we integrate from t to 1, that natural log curve. And then we're going to take that limit as t goes to 0 from the right now. So this is, again, the left endpoint discontinuity. And that's what we're looking for. This is I of t. Okay. All right. So we integrate. T is 1, natural log x dx. Let's make sure we write this. We can see this. And like I've been saying, this is x, natural log x minus x. It is good for you to know the integral of some of these classic questions from Calculus 2, how to integrate natural log. It's done by using integration by parts, in case you guys forgot. Use integration by parts. We've done that. Classic integral question. U is ln x and dv is dx, in case you guys forgot. So we're going to apply this here. We're going to need to get f of 1 minus f of t. We're applying the limits, the integral limits. So we get 1 natural log 1 minus 1 minus t natural log t minus t. Well, natural log 1 is actually 0. So we end up with negative 1 minus t natural log t plus t, because we're going to distribute this negative sign. Okay, it's going to change the signs to everything within that parentheses here. This is the I of t now. All right, now what you'll need to do here is take the limit now as t goes to 0 from the right here. We're using the definition of that improper integral. So now the limit as t goes to 0 from the right of this I of t properties of limits again. That's negative 1 minus that limit. T goes to 0 from the right. T natural log t plus the limit. T goes to 0 from the right of t. Well, this limit is actually 0. And this limit is 0 times negative infinity again. Don't forget, this is natural log. Okay, let's find out the... All right. This is what I'm saying. This is another example where we have an indeterminate product, and that indeterminate product requires us to use, well, we have to fix this, and then we use L'Hopital's rule. And so the fix, I'm going to put in black here. I'm going to write this product as a quotient where the first function is actually the reciprocal. And what you'll see is you get negative infinity, and again, t is positive, and that'll be over positive infinity. This is an indeterminate quotient in which we use L'Hopital's rule. And so by L'Hopital's rule now, 1 over t, and this is negative 1 over t squared. So we'll have some algebra to do here again. And the algebra is going to be 1 over t divided by negative 1 over t squared. 1 over t times negative t squared, which would be simply negative t. So we're really looking at the limit as t goes to 0 from the right of negative t, and this limit equals 0. Okay, very similar to the last one, where this equals, or this limit goes to 0. So again, it looks like this is going to be now negative 1 here. Okay, it's a finite value here. So this improper integral, if I erase this and this, that this area here is finite. It's the value -1. So this equals -1 here. And -1 is a nice finite value. This number is finite. So that means we have convergence for our improper integral. This converges. And this area here is the value -1. If we can see all that. Okay, so this ends the, I think we should say it's type 2 improper integrals. The left endpoint discontinuity is a case 2. And so, ladies and gentlemen, we'll go over tomorrow the case 3 improper integrals. But this is the work I wanted to share with you guys today. So you can take a look at that. That's a finite number, -1, classic questions. And I hope you guys enjoyed the demonstration here. So converges to the finite number -1. Let's see if we can highlight that. All right, there we go.